Today, our discussion will center on a novel form of dependence. As we are well aware, when confronted with numerous financial variables, it becomes particularly insightful to thoroughly investigate their interrelationships, specifically their correlation, or more broadly, their underlying dependence. We need to understand the impact on variable y if variable x shifts by a specific percentage, and conversely, how x is affected by y. This interdependency holds significant importance within the field of finance. As is our usual procedure, we will be making use of the Finance Research Gate, and our aim is to thoroughly examine the specific time series connection between
the technology sector's return and the overall market's return.
The specific method we're going to explore today, the one currently at hand, is referred to as the copula method. To properly understand its intricacies, we should begin by covering some fundamental concepts and basic principles. Our fundamental question is how two or more distinct variables tend to move or behave together. A common and widely used statistical measure we can employ to assess this relationship is correlation. However, it's important to note that correlation primarily captures only the linear aspect of their co-movement, specifically focusing on a central region of their overall statistical distribution. However, the world of finance frequently presents us with examples of phenomena like fat tails, significant crisis co-movement, and inherent asymmetry. Therefore, you may encounter a type of dependence that is quite distinct from simple linear co-movement, which is typically what a standard normal correlation would suggest. So, the dependence might actually be following a more intricate or nonlinear function, particularly when the underlying data distribution is not normal, or when we specifically observe significant tail dependence. In such a scenario, the copula method would prove to be considerably more robust and effective. Before we dive in, it's probably a good idea to establish some common terminology. Whenever we encounter the big X, affixed to the capital letter F, it indicates that we are working with a probability distribution. More specifically, it's the cumulative probability. For instance, consider the likelihood that our variable x falls beneath a specific predetermined threshold or a particular numerical value. What this essentially means is that if we possess a complete distribution for this particular variable, where such a distribution fundamentally represents the likelihood of observing each of the various possible outcomes or values that x could potentially take. So on this particular graph, we are observing the x-axis, which represents our primary variable of interest, and then along the y-axis, we are clearly showing the associated probability. A probability, as we all know, always ranges between a value of 0 and a value of 1. For instance, in this specific area, the likelihood of encountering an extremely low value is going to be quite small. For example, it might be around 0.1. However, in the central region, where we observe values that are average or quite close to the average, the probability, based on common sense, would naturally be significantly higher. This could, for example, reach a value of 0.5. Now, since we are specifically dealing with a continuous variable in this context, it is more appropriate to select any particular value of interest. Let's consider the small letter x at this point, and then we will examine the probability of observing this particular value or anything below it. This is too called the cumulative probability because what we are essentially doing is accumulating the likelihood or the probability of all possible data values that are either precisely equal to or fall below the specific target value x that you have carefully selected within the scope of your research study. For example, if we consider the cumulative probability of an x value being less than or equal to minus 2%, this concept essentially represents the total likelihood of observing any outcome within the far left portion of the distribution, specifically the probability of having this specific value, or any amount that is less than it, corresponds to 15%. Now, regarding the joint distribution, this is the situation we face. Now, addressing the concept of joint dependence, which is truly the fundamental essence of this entire lecture, it's quite simply this. We are seeking to ascertain the probability, or more accurately, the joint probability of one specific variable x being below a particular value and concurrently at that very same moment another distinct variable also falling below a certain value. Now, the specific value that we're looking at here doesn't necessarily have to be exactly the same as this other value that we have over here, simply because we could easily have two distinct variables, even if they possess two completely different scales. So that particular value might very well be quite different from the one we're observing here. So, in our current analysis, we are observing two distinct variables, considered as a pair, and our objective is to determine their mutual or joint dependence. For example, consider the question, what is the precise probability, or more accurately, the joint probability of an event occurring where we have an x value for the designated x variable that is either equal to or perhaps even less than minus 0.03, and simultaneously, at that very same time, having We are looking for instances where the y variable has a numerical value that is either precisely equal to or falls below the threshold of minus 0.04. So, to illustrate this concept, imagine we're dealing with a situation where we have two distinct variables, specifically x and y, to consider. And what we are essentially trying to determine here is the combined likelihood or the joint probability that both of these particular variables will fall below a specific threshold value simultaneously. The probability will appear lower than the individual probability because the coincidence of both happening at the same time below a certain value, of course, will be lower. This concept illustrates the joint dependence, which essentially means that a particular value is either falling below a predetermined threshold or conversely rising above that specific point. The term joint in this context highlights this simultaneous condition of the underlying dependence. For instance, let's consider this critical value to be 8%. So we're looking at an 8% probability that the variable x will be less than, specifically, negative 3%, and simultaneously the y variable will have a value that is less than negative 4%.
This is simply the dependence analysis, a fundamental process for uncovering the intricate connections between various components. You can even take this approach further, delving into the subtle implications and potential impacts of these interdependencies.
The probability extending in a certain direction. For instance, from -1 to infinity. In any case, we are simply covering the joint probability, where the probability itself is the accumulated probability, or more precisely, the area under the probability graph. So for now, just try to really remember these two very important terms that we're discussing at the u and the v. Now the u, as we've clearly mentioned before, specifically represents the accumulated probability of having a value that is either below or precisely equal to x. So please just make sure to keep this particular example firmly in your mind. It's quite crucial for understanding. So, for example, this u here, it represents the entire area, which is essentially the accumulated probability of each individual point within this region. Therefore, any value that falls below our defined threshold inherently possesses a certain probability. And what we're doing is we're essentially summing up all these individual probabilities for every single value located within this specific area. So when we perform this operation, it's essentially like calculating the area under the curve in this specific region. We apply the exact same principle for the y-axis, meaning we consider any y value that falls below a particular threshold or point we've defined here.
This forms a crucial part of our overall analysis, allowing us to determine the precise probability. The result might be quite a small figure, for instance, representing just a single person or perhaps two people, or indeed any other quantity. Crucially, we are working with a spectrum of continuous values in this scenario.
So we sum up the probabilities for all values that fall below a specific threshold. This is precisely equivalent to determining the area under the curve at that point. Therefore, the area here corresponding to x is designated as u, and the accumulated probability or this specific area is referred to as v. It's important to remember this as you'll be using these concepts quite frequently. And of course, because it's a probability or accumulated probability, it shouldn't exceed 1. And of course can be less than 0. So it should be between 0 and 1. The central idea of a copula is this. A copula function is essentially one that joins separate marginal distributions to create a single joint distribution. So when we are presented with the terms f, x, and y, it means that we are carefully examining the joint probability, just as we have mentioned previously. Therefore, this particular joint probability is precisely what we formally refer to as the copula, which is always denoted with the capital letter C. For example, in this specific instance, that would clearly represent the u variable, and this in turn would represent the v variable. So the capital F specifically will indicate to us the precise location of the x value within the overall distribution of the x variable. It also shows its placement within the distribution of the y variable, which, as I've already explained, is consistent with what was previously discussed. If the variable u, for example, represents a value of, let's say, 10%, this indicates that our focus is on the lower segment of the overall data distribution. Similarly, if the variable y, for instance, also happens to be 10%, then what we are truly examining is the extreme left tail of that same distribution, specifically focusing on the lowest 10% of all the recorded observations. It could be as low as 15 or perhaps as high as 18. They don't necessarily have to be the same value, by the way. For example, if u is 0.2, v is 0.1, it means we're interested in the lowest 20% of the x variable. First, we're considering the lowest 20% of the entire distribution of our x variable. Subsequently, we're particularly interested in the lowest 10% of the y distribution values. Therefore, what is the probability of having both of these specific conditions occurring simultaneously? At the lowest distribution of each respect, that is, each individual aspect
regarding each variable.
So, at this particular moment, the probability of both outcomes falling below, or precisely at the lowest point of the distribution, is exactly 7%. Now, it's quite interesting to consider how this specific value compares to a scenario where these two events are completely independent. What is the probability of observing the lowest 20% of the x variable's overall distribution and at the very same time the lowest 10% of the y variable's distribution? If these two events are not dependent on each other, or if they are truly independent, then we can simply multiply their individual probabilities together. Let's consider the probability equation. If you have two independent variables or events and you want to determine the probability of both of them reaching specific values at the same time, as long as they are truly independent, you simply multiply their individual probabilities. For instance, if you multiply this value with that one, the outcome will be just 2%. Now, if the level of copula dependence, which essentially represents the joint dependence, or alternatively, the joint probability, is observed to be higher, this indicates that there exists a clear relationship or, indeed, a significant level of dependence. So, a 7% figure indicates that there is a 7% chance or likelihood that both variable x will fall within a specific range of its lowest percentile values, and simultaneously, variable y will be observed to be lower than a particular threshold value, with both these conditions happening concurrently. So once more, this represents the copula, which is essentially the joint probability that we previously discussed. For instance, the final recorded value stood at 7%. You can observe that this particular 7% value, which is shown right here, corresponds precisely to what we define as the copula dependence. For example, let's consider a scenario where we might ask you to identify or compute the copula dependence of the variable u. This variable u, as you can see, is intrinsically linked to our primary x variable. And then similarly, we would also be looking at the y variable, which we have designated as v. So, in this particular instance, we are specifically asking about the probability of observing the x variable's value within the lowest 25% of its entire range, or its complete distribution of possible values. This phenomenon is occurring simultaneously with the y variable, specifically when it falls within the lowest 60% of all its observed data points. The probability of this specific event occurring, or degree of dependence observed in this context, is precisely 22%. So, you would multiply 25 by 0.6, and that result will give you the expected value if there is no dependence present. Then you can compare it with the copula dependence. If that value is higher, it indicates that we have a significant dependence. You can then multiply these two values together, and that will give you exactly 0.15. So, yes, the level of dependence that we are observing in this particular case is significantly higher than the value we would obtain if there were an entirely independent relationship between x and y. So, to provide another clear illustration, consider a situation where the x variable's probability distribution is specifically at the 0.3 mark. This essentially means that we are focusing our examination on the lowest 30% of all the possible values that x can take. This naturally refers to our designated x variable. So the lowest 30% of the x values are clearly located right here. And for the other variable, we are going to be examining the lowest 40% of its range. So you can then proceed to draw a similar distribution of values for the y variable, and then you would simply take the lowest 40%. Let's consider point number 4. Now we need to determine what the probability would be of observing the lowest 40% of the values associated with y, and simultaneously the lowest 30% of the values for x, occurring at precisely the same moment, or concurrently. If these events are truly independent, you would simply multiply the probabilities, 0.3 by 0.4. The resulting chance is 12%. If the variables are independent,
If you determine that the estimated copula dependence value is found to be significantly higher than this particular reference number, it clearly signifies that we are observing a strong positive dependence. However, if the copula provides a numerical outcome that is notably smaller than the specific value of 0.12, this would then indicate that the existing association within that particular region is considerably weaker than what would be expected if they were truly independent. So let's now proceed to a more in-depth discussion regarding the topic of copula density. It's important to note that the term copula density, as used in this context, is distinct from what we typically understand as standard probability or even the concept of accumulated probability. In this specific instance, the notation of a small letter c is employed to represent the concept of marginality. Marginal, in this context, refers to understanding how the overall probability distribution or the intricate copula dependence shifts and reacts if we were to slightly adjust the values of u and v. Remember, the u represents the cumulative probability. It's cumulative, meaning it encompasses a specific area under the curve of the probability distribution, and it's defined as cumulative because it doesn't just give you the probability of one exact specific value, but instead it calculates the probability of that value or any value that is less than it. So what we're observing here is that it's encompassing a particular region within the overall probability distribution. For instance, this specific portion right here is designated as U, and then this other distinct region over here is labeled V. Now, the crucial question is, what precisely would be the outcome if we were to make a slight adjustment to this area U, and then concurrently at that exact moment also introduce a modification to V? What will be the ultimate effect of this copula dependence? So, essentially, we are determining the differential, which is fundamentally the rate of change, or more precisely, the change in y relative to the change in x. Here, our y specifically represents the copula dependence. For instance, consider what might occur if we were to adjust the u value, specifically the cumulative probability of x falling below a particular threshold, shifting it from 0.2 to 0.21 by just a small increment. Simultaneously, imagine we also increase the cumulative probability of y, moving it from 0.3 to 0.31. Let's consider the probability in this scenario to be this specific value, for example 0.0015. Now, if this represents the resulting change that we obtain by merely increasing the variable u by a single percentage point, so for instance, let's assume we've adjusted this value upward from 0.3 to 0.31. Alright, so we took that particular figure and we increased it by just a modest 1%. And then for this section here, we're also going to raise it by the same 1% again. So what we did was that we increased the denominator of this equation by just 0.001, and we observed a change in copula dependence. Naturally, it will go up because we simply increase the likelihood of these two variables occurring simultaneously since we expanded the area. I mean, if you consider the entire thing, then the copula dependence will be 1 because you've included all values for both variables. So as we increase the area, of course, the copula dependence will go up. And in this case, it went up by 0.0015. Considering the increment in x, which represents the variation in u, and the variation in v, this calculation will then provide you with a specific ratio, which in this particular instance is 1.5. This value is technically referred to as the marginal density. And it's more than just a single factor. This implies a significant level of dependence. If this value is 1, it indicates a state of independence. This is because even if you were to increase the values of y and v, the copula's dependency would not increase by a significant amount. Therefore, we observe a more independent relationship. However, in this specific case, we do not see that because the value is 1.5. This clearly signifies that yes, we indeed have a strong dependence relationship. So even if we increase the area of u and v, and as a result the copula's dependence would naturally increase, it actually went up by more than 1. And what this truly indicates is that we possess a very significant level of copula dependence. Consequently, the local density that we observe in this specific location is quite distinct from the overall characteristics of the entire area. The density we observe in this context fundamentally explains what will occur if we were to incrementally increase the numerical value of a specific variable, whether it's x, y, or indeed any other relevant parameter, and then crucially, what impact that adjustment would have on the corresponding area. To provide a clear example, let's consider selecting a particular interval within a given statistical distribution. If we were to slightly expand its current width, how would that then directly influence its corresponding height or magnitude? That is the density. For example, let's take the specific number 8. So if you were to increase x by just a single unit, so if we consider the height at this specific point, or alternatively the probability value, it will increase by 8 units. Therefore, what we're talking about here is essentially a differential, a distinct increase. Wouldn't you agree? We're not referring to the entire area under the curve, but rather specifically to the incremental change within that area, or more precisely, the change in that probability itself. Here, its significance is 8. So if you were to increase the x just a little, the area would then go up by 8. For each single unit, it'll go up by 8, but here, it'll go up by 5. The copula dependence is essentially the same idea, but you're simultaneously moving both variables at the same time, just as we did in this particular example. And here we also have a significant value of 1.4. So if you have these numbers, you can then multiply them together, and that will give you the joint density. We're not looking at the copula dependence in this context. Instead, our focus is on the joint density. This metric is crucial for understanding the underlying relationship between these two specific variables. A higher value here signifies that the two variables are moving together, indicating a much stronger, more pronounced directional correlation. So a density, by its very nature, is not the same as a probability. And therefore, the copula density has the ability to either raise or lower the joint consideration, especially when compared to a state of independence. Given this, how then can we accurately determine the precise number of copula dependence? We have a variety of different models available to us. One of the models we can utilize is known as the Gaussian cocopula, and its very name clearly indicates that we are employing the normal distribution, which is also referred to as the Gaussian distribution. Within the framework of this Gaussian distribution, you simply need to select the appropriate u and v values. You have to pick that. For example, if you want to examine the dependence, specifically the joint dependence between variable x and variable y within the lower tier distribution, then, for instance, you might choose a value like 0.2, perhaps specifically 0.2, or even 0.25, or possibly 0.3, and at that point, you would be stating, what exactly is the concept of lower tail probability dependence when we consider the relationship between two distinct variables, x and y? For instance, what is the specific probability of observing the variable x falling within its lowest 20% range, simultaneously with variable y also being found within its lowest 30% range? Right. So how do we go about finding that? In our previous examples, we provided the number, but how can you determine it here? If you're using the Gaussian, then you simply follow this equation. So you would take any specific probability or a particular segment of the overall distribution that you're currently focusing on. Then you proceed to calculate the inverse of that value. What this essentially means is that you are determining the specific z-score or z-value which corresponds to and provides the probability for u, which in this particular instance is 0.2, and also for v, which is directly connected to y, and in this scenario it's 0.3. And then you ask for the z-value. It's important to remember here that z-values tend to rise and u and v represent the probability. So basically you're saying that if you're interested in identifying the observations that fall within the lowest 20%, then what z-score would you need to find that specific threshold? This isn't the raw original x value that we typically start with. Instead, it has been transformed and standardized. So this specific standardized value is designed to precisely identify the threshold that marks the lowest 20% of the entire data distribution. For instance, if we consider the median, which is 0.5, representing the exact center or the left half of the distribution, then the corresponding z-score will be precisely 0. That's a fundamental concept we're all quite familiar with. So the inverse operation will yield the z-score, which in turn provides the probability or the cumulative probability for both x and y. And once you have obtained these values, you then proceed to determine the joint probability of z being below a specific threshold and the other variable's z-score also being below its own specific value. And that will give you the advantage. We're using a copula primarily because the resulting joint probability calculation will consistently yield a numerical value that always falls somewhere between 0 and 1. For instance, if we look right here, we can see, oh, actually, we already have a clear example laid out for us right here. Imagine for a moment that regarding variable x, you are interested in studying the lowest 10%, and for variable y, the lowest 20% of the entire distribution. And it was stated that the dependence you initially assume is a value of 0.5. First, what is the equivalent z-score for our variables, u and v, in this specific context? We understand this because at the lowest joint, which represents the very lowest part of the entire distribution, the resulting z-score will inherently be negative. This is due to the fact that the z-score itself is a standardized value, not the raw original x variable. It is, in fact, the standardized version of x. So, the very center point will be 0. For example, here it could be something like 3 minus 3. This is essentially the Gaussian, what we call the normal distribution curve. So, if you are considering the lowest end of the distribution, then the most likely outcome is that the corresponding z-score will, without a doubt, be a negative number. For instance, it could be a specific value such as 1 minus 1.2. And the good news is that Excel can very easily calculate this for you, and it can also provide you with all of these relevant values. So, for instance, you have the capability to query Excel directly, asking it to determine the specific z-score that corresponds to encompassing or accounting for the bottom 10% of your data distribution. In this particular scenario, the calculated z-score turns out to be negative 0.12. Therefore, the precise numerical value we are considering here is negative 1.2816. This means that any data point falling below this specific z-score effectively covers or represents the lowest 10% of your entire dataset. We'll apply the same logic to the other variable. At 20, then the z value will naturally become larger because we are now covering a greater area. So the value is effectively increasing, and consequently, the z value here will be larger or perhaps less negative, specifically minus 0.8416. Once you determine the values for Z1 and Z2, your next step is to ask what exactly is the bivariate normal cumulative distribution, and that particular calculation will then provide you with a specific outcome, for example, a result of 0.5, assuming a 0.5 correlation. So when we consider the bivariate normal cumulative distribution function using these specific Z values, we find that its approximate value comes out to be 0.062. So, the probability of observing X within its lowest 10% range and concurrently Y falling into its lowest 20%, specifically the lowest 20% of all possible values for Y occurring at the very same moment, is precisely 0.062.
So, there is a 6.2% chance that both of these transformed variables, x and y, are jointly distributed following the Gaussian copula with a dependence parameter, or a Gaussian copula correlation, that is equal to 0.5.
If they are independent, then you would simply multiply those two numbers together, and that would give you a probability of 2%. So yes, there is a significantly higher chance under the Gaussian copula that both of those values will be found in the lowest tail of the distribution, much more so than if they were truly independent. So, purely by random chance, we might expect it to be around 2%. However, the actual observed figure indicates it's significantly higher, at 6.2%. This suggests we're dealing with a lower tail dependence between x and y.
Now, the Gaussian copula is quite good and it's widely employed in many situations. However, it's not really suitable if you're dealing with truly heavy tail dependence. You see, this is primarily because we are inherently following the Gaussian, or more precisely, the normal distribution. And as we know, the normal distribution simply does not possess those characteristics of heavy tails. So if you have tail dependence, you're not measuring the actual dependence correctly, and therefore you're going to end up with other functions. These other functions look like this particular thing here. You can measure the lower or the extreme dependence, like the lower tail dependence, if you follow this specific equation.
And by performing this step, you will effectively determine the lower tail.
Let's discuss the concept of probability. So, for example, if we consider Q, which as you know is inherently a very small numerical value, because we are specifically focused on measuring the extreme lower tail of the distribution, let's just say it's 0.01, representing, for instance, the lowest 1% of all possible values for Y, and likewise the lowest 1% of all possible values for U.
So, if we consider x to be extremely bad, which is what we're looking at here, what is the likelihood or the chance that y would also turn out to be extremely bad?
So what we're really looking at here, what we're trying to uncover, is a concept known as extreme tail dependence. To put it another way, if our variable x experiences an extremely negative outcome, perhaps falling into the lowest 10% of all its possible values, what then is the probability or the likelihood that our variable y will also exhibit an equally extreme poor performance? And this is exactly the kind of interconnected relationship we are attempting to identify and understand. So, what we're essentially doing here is measuring the likelihood or the tendency for two different variables to both become extremely low, specifically in the lower tail of their respective distributions. If one particular asset crashes badly, as you can observe right here, how probable is it that the other asset will also crash severely at the same time? For example, consider this scenario. If you possess these specific values, then you can observe here the copula dependence, meaning if both events are happening at the same time, the overall chance, the precise probability, is exactly 0.004. Let's consider a scenario where we have a value of just 0.01. If you then calculate the ratio using this specific equation, you would simply take the value of 0.004 and divide it by 0.01. The result of that calculation will be 0.4. Now, what exactly does this result signify? It implies that we are looking at a situation where one particular variable is performing at its absolute worst, specifically within its lowest 1% range.
So, if x, for example, is in the worst 1% of values, the other has about 40% chance of being in the worst 1%, which is y, the other variable.
So, once more, if x falls into the worst 1% of all possible outcomes, there's a substantial 40% probability, and this particular finding is quite significant, that the other variable will also be found at its absolute lowest 1%. This clearly indicates a very strong crash dependence between them.
You can also consider taking into account the upper tail dependence.
How can you possibly achieve that? It's quite straightforward. You simply adjust the Q value. Rather than having a value of 0.01, let's consider you now have a value of 0.99. So here you are going to the upper tail, and you do the same calculations.
So that will give you the upper tail if you increase Q, for example, to 0.99.
other form of copula is you're not following a distribution, you're following some sort of functions, like the Archimedean copula.
There's a generator function, this symbol here, which is known as phi. I'm not entirely certain what we might call them, but there is a particular symbol right here which we use, which is the generator function. The underlying dependence actually arises from the way that particular function distorts or bends the space. Therefore, this dependence is effectively established by employing a shared or common transformation scale. In the case of the Gaussian copula, we simply utilize the normal distribution and its z value to accurately determine the probability. However, in this specific context, we are employing a different kind of mathematical function to achieve our goal. The inverse operation here at the conclusion will make certain that it brings whatever calculations you're performing back to 0 and 1. Because remember, copula dependence is fundamentally a probability, and that should always be strictly between 0 and 1. We currently utilize 3 distinct versions of the Archimedean copula. Specifically, these include the well-known Clayton, Gumbel, and Frank models. The Clayton copula in particular focuses more on lower tail characteristics. It demonstrates a much stronger performance and relevance within that region. Well, it becomes particularly useful in situations where the combined negative results or consequences are considered to be more significant than any combined positive results. This is especially true when there's an inherent imbalance or asymmetry in the situation, and that kind of asymmetry is far more likely to occur if you find yourself facing a greater number of undesirable outcomes compared to the favorable ones. In such specific circumstances, that particular copula would indeed be the most appropriate choice to employ. And we're going to be using this particular function, correct? The u and v are the specific parameters that the user is actively selecting. As I've mentioned previously, for example, we could be looking at the worst 10% in this group or perhaps the lowest 20% in that other category. The parameter we're considering here, for example, could be 2, but it must be greater than 0. You then input these numbers into a simple mathematical function, and the outcome ultimately will be a number falling between 0 and 1. It absolutely needs to be within that range, between 0 and 1. For instance, if you have a set of these specific numbers, you then plug them into the equation step by step.
This is the point.
And you end up with this specific value, 0.16. Is this result truly significant? You compare it, especially if you have independent samples. If you have independence, then you multiply the two numbers together. The result is 6%. It's quite clear the copula dependence is significantly higher. In this specific case, the Gumbel distribution, as we've discussed, is fundamentally a mathematical function. We are utilizing the natural algorithm specifically for the theta parameter. You mentioned theta must be greater than 1, and then you simply plug in all the necessary numbers. And then, at the very end of the calculation, well, it really ought to fall somewhere in the range of 0 to 1. The Gumbel copula in this context specifically emphasizes an upper tail dependence rather than a lower tail dependence. This makes it particularly suitable for situations where joint booms or other joint high outcomes are more strongly linked together. For instance, this would apply when you are specifically picking out the higher values from a probability distribution. If you input the figures and perform the necessary calculations, you'll find that you arrive at a copula dependence value of 0.78. This particular result is quite significant. However, if we consider the scenario where they are truly independent, the value drops to 0.72. So, let's look at the probability of variable x having 8% or less of its total values, and concurrently, variable y having 90% or more of its total values. The calculated probability for this specific scenario is 0.78. This particular value is, in fact, significantly higher than it would be if these two variables were completely independent. The final model we are discussing is the student's t-copula. In this specific case, we are utilizing the t-distribution. This is the key difference here. However, the fundamental idea remains quite similar. We are calculating the t-values for both u and v instead of using the z-scores. So there is a fundamental difference between the Gaussian distribution and the student's t-distribution. As we are aware, the t-distribution inherently possesses much fatter tails, indicating a greater likelihood of extreme observations and thus exhibits a reduced degree of normality. Therefore, while it is quite similar to the Gaussian copula, its key advantage is that it simply allows for a much greater level of tail dependence. This is, in fact, the primary and most significant distinction between the two. So let's apply this using our website. We'll begin with the time series data. And then, for instance, we would proceed to select the year 2000, followed by 2024. After that, we just hit apply. First, we'll choose a specific monthly return for a single stock, and then we will systematically apply that chosen return across every single firm in our analysis. Through this process, what we are essentially doing is calculating the median stock return observed across all of these firms, and this in essence represents our determination of the overall market return. So ultimately, our objective here is to precisely identify and quantify that crucial market return. Please note that I've intentionally left these particular boxes blank, which signifies that I'm including every single firm available, and our objective is to calculate the monthly stock return for each one of them. The chosen method for aggregation is the median value, meaning that for every single month, we meticulously determine the median return across all of these included firms. This resulting figure is what we refer to as the market return.
And then we are going to create the sector return, because the exercise is about the dependence between the market return and the sector return.
So,
I am currently attempting to locate the appropriate sector. Let's select technology and then apply it. We should rename it, and then once we finish constructing the X and the Y components, we'll then be in a position to thoroughly examine their dependence.
Then we build a combined data set in order to make progress.
If you scroll down a bit further, you'll find the Specialize and Advanced section, and within that, you'll see the copula options. You can then select X, which might represent, for instance, the market, and Y for the other return sector. Among the choices presented here are the Gaussian distribution, student's t-distribution, and various others. For now, let's begin by focusing on the Gaussian. So, if you're looking to carry out a simulation, the primary question, or Q, as we brought up during our previous conversation, pertains to the notion of tail dependence. Do you recall our earlier conversation when we specifically brought up the concept of the 1%? That was back when we were really digging into and trying to understand the complexities of tail dependence, wasn't it? Well, this is exactly what we were talking about.
But we can definitely hold on to that.
So we need to keep that at 5%, all right? And then from there, we can fit and find the copula dependence. All right, so in front of you, we have the complete original data set. Following that, you'll also observe the uniform data, the percentile, and then the U and V values. To illustrate, this particular section right here represents the U. So we are essentially converting each individual value to its corresponding position within the overall distribution. For instance, if a value is negative, its associated probability will naturally be quite low. However, if we encounter a significantly larger value, then its probability will consequently increase. Therefore, we're mapping every single value to a range that lies strictly between 0 and 1. If the original value is small, it will then approach a position closer to 0. If the value is quite substantial, it will be much closer to 1. These are the U and V variables that we had specifically mentioned earlier in the notes. So, this process will yield the copula dependence for you, and the result is 0.85. That's a very strong correlation. Yes, it truly is quite strong. You'll observe quite clearly that in this specific scenario, we completely lack both lower tail dependence and also upper tail dependence. This particular observation represents the theoretical expectation. Based on the principles of the Gaussian copula model, one would not anticipate finding any significant tail dependence whatsoever. However, the actual empirical data clearly demonstrates the opposite, indicating that specifically in the lower tail, we observe a very significant level of dependence, precisely at 0.46. However, the upper tail dependence is notably stronger. This implies that both the market's return and the technology sector's return exhibit a greater reliance on the upper tail, particularly during periods of significant positive returns. In these instances of large gains, the correlation is more pronounced compared to situations of lower tail dependence. However, this observation does not suggest that if the broader market experiences a downturn, the technology sector will necessarily avoid a similar decline. When we consider the technology sector, the probability of its returns experiencing a significant crash is calculated to be 0.46, and this is specifically if the broader market return goes down. So, to be clear, if the overall market return does indeed crash, then the specific probability of the technology sector also crashing is 0.4 or 46%. You can easily download all of the tables right here by simply clicking on these links. Now, if for any particular reason these links aren't functioning correctly, you can navigate to this specific page, then click this button, and then click this one. And from there, you'll be able to download the file. For instance, right here, I've already obtained...
We need to identify the u and v components, or the specific values for each variable.
And here we have the original variable.
You are permitted to modify and choose a distinct family arrangement as we previously indicated.
So that will be everything for today. Thank you for listening.